Hey everybody, welcome back. Today we're going to be going into a little bit more detail about the circuit model, and also I'm going to be showing you your first two quantum algorithms. Specifically, I'm going to be showing you quantum teleportation, as well as its dual, superdense coding, which are two protocols to transfer quantum and classical information between parties. But before we get started with that, I'd like to begin by once again reviewing all of the notation that I've subjected you all to so far. So again, recall that the most important thing that we've done is we've come up with a linear algebraic encoding for numbers. So for example, the running example I keep on giving is 5, which in our old notation, we would express as E1 tensor E0 tensor E1. In Dirac notation, we, again, use 0 equals E0, and 0, 1, for example, is equivalent to 0 tensor 1. All right? So, again, this is in Dirac notation, either 1, 0, 1, which we can also write as 1, 0, 1. Another thing that I should note, which I'm not sure is 100% clear, well, there was a huge waste of space when it came to representing a number like this as a vector. Like, for example, if we were to represent this number as a vector, it would be 1, 0, 0, 0, 0, 1, 0, 0. Okay? There's a lot of wasted space in that, obviously. But if we have a distribution over this, we could end up having a state. Let's say the most general 2-qubit state we could have would be sum over I, AI, I in Dirac notation, which is equal to A0, A1, A2, A3, where each of these AIs must be of the form square root of some probability and a phase up here, okay? Where, again, the sum over all PI has to be equal to 1. All right, and so that's basically Dirac notation in a nutshell. So let's go through and remind ourselves how we would manipulate a quantum state vector like this on a quantum computer. Well, what we would do is we would carry out a series of gate operations. So I had a question the other day, and I figured, well, it might be a good idea to re-emphasize this. Let's say want the NOT gate. Okay, the NOT gate can be is also expressed as X or poly X in this case. And what it does is in Dirac notation, it maps 0 to 1 and 1 to 0. Now, this actually is this mapping, this is completely enough to specify the action of the map. The reason why is because of the fact that the computational basis is complete. So that means every vector can be written in terms of the computational basis. Just like I did up here. This is an arbitrary vector, and this is its representation as a sum of vectors in the computational basis. So it's complete, but also all operations save measurement in quantum computing are linear, which means that we can, if we apply a gate like X on the sum over I, AI, I, this is equal to the sum over I, AI, X, I. All right, and that is enough in order to specify the action. So we can figure out the matrix representation of non, and again, I'll do this example in Dirac notation, by using the fact that every matrix M, let's say I j in Dirac notation is equal to bra I m j, like that over there. Okay, so then, in that case, we can just work out the matrix elements one at a time. M0, 0 is 0, M0, which in this case is the same thing as the inner product between 0, x, 0, which is 0, 1, equals 0. Similarly, M11 is 1, M1, which in our case is 1, 0, which is 0. Similarly, if we find a matrix element for x0, 1, we end up finding it's the same as x1, 0, which is equal to, say 1, x, 0 equals 1. Therefore, the matrix representation for naught in the computational basis is 0, 1, 1, 0. All right, so that's how you can figure out the its representation in the computational basis. Similarly, we can express this in Dirac notation just by noting that the matrix, say 0, 1, 0, 0, that is equal to 0 outer producted with 1. If you just do the matrix multiplication between these two vectors, you'll note that you end up getting this. And so, using this rule, we can end up seeing very straightforwardly that this matrix actually can be expressed in the form of this plus 1, 0, where I use this thing which some people will think is an x just to be a faster way of writing this over here. So that is how we can come up with algebraic representations of matrices using Dirac notation. Now, the unitaries that are going to be most useful for our purposes are the following. First off, there of course is the NOT gate, which in the computational basis is 0, 1, 1, 0. And then there's the Hadamard gate, which is equal to 1, 1, 1, minus 1, divided by root 2. Then there is poly z, which is a little bit different. It's a way of getting a minus sign in. And then there's poly y, which is equal to 0 minus I, 0. Okay. Other commonly used gates include the S gate, which again is the square root of the Z gate, which is equal to 1, 0, 0, I, because the square root of minus 1 equals I. Then there's the T gate, which is the square root of S, which is equal to 1, 0, 0, square root I, which, of course, is equal to 1, 0, 0, e to the I pi by 4. Okay, so those are a set of single qubit operations, but another one that is of great interest is the RZ gate, which is of the form e to the minus I z theta over 2, which is, when you represent that, e to the minus I theta over 2, 0, 0, e to the I theta over 2. So this gate actually generalizes a number of gates. By choosing theta correctly, you can make z out of this, you can make s out of this, you can make t, and a bunch of other gates, because this is a continuous gate. As I mentioned, this gate makes a lot of sense experimentally, and it'll make our lives really easy. It turns out that this gate over here can be approximated actually using sequences of Hadamards and T gates. And I'll get to an explanation of how that works later, but a detailed proof I think is challenging. But in any case, that is what we these are the set of single qubit gates that are most commonly used in order to be able to describe our transformation. So let's begin by showing some properties. First off, all of these gates, as I mentioned before, are unitary, meaning that x inverse, for example, is equal to the x conjugate transpose. And actually, many of these gates are also Hermitian. A Hermitian operation satisfies x, or let's just say A equals A dagger. So many of these operations are both unitary and Hermitian. So unitary and Hermitian implies A inverse equals A dagger equals A. So A equals A inverse, and also its transpose. So an example that you know is the NOT gate squared is equal to identity. If you go through and do the algebra, it's also actually easy to see that the Hadamard gate squared equals identity, and it's also poly z squared equals identity, and poly y squared equals identity. The remainder of the gates that I drew up here, most of them are only unitary. Like this, for example, S, T, and RZ in general, those are only unitary and not Hermitian. The rest of these guys over here, these are both unitary and Hermitian. So, those are some neat properties. Okay, great. Let's take a look at manipulating some of these objects. So, there's a couple of neat properties and important ones that I think are, give you some good intuition for how Hadamard and how the rest of these gates can be used and actually interconverted. So it turns out that we actually don't need the X gate technically if we've got the Hadamard gate and the Z gate. The reason why is because of the fact that it turns out that HZH equals X. So a way of looking at this is Hadamard is the matrix that interconverts the NOT gate and the poly Z gate. Or another way of looking at it is that poly X ends up flipping a bit from 0 to 1. Poly Z, if you put a 1 in the input, ends up going to -1. 1. So you can see this is kind of a phase flip, whereas the other one is a bit flip. So the Hadamard gate allows us to interconvert between storing the data data and the operation that we want in the bit value versus the phase value. And actually we'll see that this is because of the fact later that H is a 1 qubit Fourier transform. And so this is actually, for those of you who are familiar with Fourier transforms, this is a direct consequence of how Fourier transforms ultimately work. So, great. That is how the operations end up going. Now, let's prove this. So we have HZH. Easiest thing to do, because we don't have too many identities at the moment, is let's just actually express all of these guys as matrices. Now, because I don't want to keep on drawing factors of 1 over root 2, I've factored both of the 1 over root 2 factors outside the matrices. Okay, and so now the matrices are of that form. So let's do the matrix multiplication. I'll start from left to right. So, multiplying row 1 by column 1, I get 1 minus 1, 1, 1 over here. And now multiplying that through by 1, 1 minus 1, I end up getting that this is 1/2 0 over here, 2, 2, 0. And that is poly X. So we have now that HZH equals poly X. But also, we end up getting that Z equals HXH. So the Hadamard operation can be used in order to convert X into Z and also Z back into X. So to see this, well, all we have to do is take this initial expression up here and apply Hadamard transform again to it. So if we have HZH equals X, well, I can apply a Hadamard transform to both sides of it. Now, using the fact that the Hadamard is Hermitian and unitary, we end up getting that H squared equals identity. Therefore, Z is equal to HXH as well. Okay, cool. So that gives you a good way of interconverting those. Now, as I've mentioned before, there's some other properties with the poly operations that are really useful. The first property is that if we can actually end up converting poly X and Y into poly Z. So XY equals IZ. All right, and let's just actually do the arithmetic again in order to work this out. So recall, poly X is our favorite gate so far. Well, maybe the identity is our favorite gate, but this is a close second. So what we do is we then do this matrix multiplication. Now, when I carry this out, I end up getting I over there, 0, 0, minus I. And that is IZ. Now, it's possible, actually, to apply the exact same reasoning and verify that this expression also holds under cyclic permutations. So, for example, ZX equals IY, and YZ equals IX. Okay, I guess I just showed off that I'm Canadian. My apologies. That was also very Canadian, I suppose. But anyways, these are our expressions for that we can use in order to be able to show that operators, that the product of two distinct poly operators ends up creating the third. So interestingly, what this ends up meaning, if we've got poly operators, then they end up forming kind of a closed group. If we keep on multiplying poly operators over and over and over again, we can't generate anything that isn't a poly operator. Because, for example, best we can do is map X or Z to Y, X, or if we multiply it by Z again, then we can get identity. So with the poly operators, it forms a closed group. We cannot generate anything more than the four basic poly operators by multiplying with each other. And this is the reason why we have these additional operations, which allow us to go outside of the space of poly operators, which is needed if we want to have every unitary operation. So those are our operations. The next fun fact that's important is that we have xy plus yx equals 0. This property over here is known as anti-commutation. So two matrices are said to commute if AB equals BA. And anti-commutation ends up implying that AB equals minus BA. Anti. All right. So and it turns out that this happens for any pair of poly operators. For example, xz plus cx equals 0, and so on and so forth. I recommend that you go through and prove to yourself that these expressions hold, because it's a good exercise, and also it's pretty straightforward. And finally, I should mention that the RZ gate actually can be used in order to be able to implement basically any of the S or Z gates. For example, RZ of pi is equal to Z. Now we can see this because of the fact that RZ of theta is equal to e to the I theta over 2 e to the I theta over 2, 0, 0. So if we put pi in, then what we end up getting is e to the minus I pi by 2, e to the I pi by 2, and this is equal to minus I 0, 0, I. Okay, and this is equal to minus I 1, 0, 0, minus 1. Okay, and so this is equal to minus I Z. Now, recall that the unitary matrices in quantum mechanics are only defined up to an arbitrary phase. The reason why is that the probability of a given outcome, P of I, that's equal to absolute value of I times the wave function squared. Okay? Again, and this is just a form of the fact that the wave function can always be expressed as P naught e to the I theta naught all the way down. So I'm just using that expression in here. So the fact that it ends up going like the absolute value squared, if I multiplied all of these elements by minus 1 all the way down, then we'd have a minus sign out there, but the absolute value squared gets rid of it. So any constant, including -1 or e to the I theta more generally, ends up being irrelevant. So we can take this part out because the absolute value of I equals 1. And again, for those of you who've forgotten how to do the absolute value of Z, the absolute value of Z for any complex number of the form x plus iy is equal to x plus iy times x minus iy square root. Okay, so that is that. Also, I should mention another thing, that if we want to rotate a quantum bit through some arbitrary angle and change the amplitudes, we can do that by implementing this rotation of rx theta, which is equal to e to the negative I theta over 2 poly x. And this is equal to Hadamard e to the minus I theta over 2 z Hadamard. Okay, well, let's prove that. The easiest way to prove this is, again, using Taylor's theorem. So if we use Taylor's theorem and we sum this all up, we end up getting minus I theta over 2 z to the j over j factorial. And again, I've got these Hadamard operations outside. Now, note that if we expand this out, what we end up getting is we would end up getting I minus I theta over 2 Hadamard z Hadamard minus theta over 2 squared over 2 factorial Hadamard z squared Hadamard. But we can re-express this term as Hadamard, Z Hadamard, Hadamard, Z Hadamard. The reason why is because Hadamard is Hermitian and unitary, so both of these multiply together to form the identity matrix. So we can express this whole thing by grouping the terms accordingly as negative I theta over 2 HZH to the j over j factorial. But recall that as we ended up showing previously, j equals 0 to infinity of negative I theta over 2 x to the j over j factorial. And recall from the definition of a matrix exponential, this series is defined to be negative I theta over 2x. Also, using the fact that x squared equals identity, this whole thing can be resummed, and it's easy to see that this is cosine theta over 2 identity minus I sine theta over 2x, which ends up giving you a matrix of the form cosine theta over 2 minus I sine theta over 2 minus I sine theta over 2 cosine theta over 2. Okay, cool. So those are a set of useful operations that we can do on single qubits and many of their relationships. Something that we're going to see later is that any unitary operation, U, can always be expressed in the form e to the I delta RZ of alpha Rx of beta RZ of gamma for parameters delta, alpha, beta, and gamma. Okay? So that is one of the reasons why we're interested in Rx, and when I explicitly prove universality for these operations, we're going to get reintroduced to Rx with a vengeance. But for the moment, I think that's most of what we end up needing for single qubit operations. All right, cool. So now, let's start talking about 2-qubit operations. Again, with 2-qubit operations, the only truly unique the only truly different operation that we need for 2 quantum bits is actually the controlled NOT gate, which is of this form, which we can view as a reversible XOR. So, for example, if we've got a state A up here and a state B down here, this will end up mapping us to A and A exclusive or B. And recall the Toffoli gate, which we spent a lot of time talking about, in this notation can be expressed as this, where each of these refer to the controls, and this is the target, the one that gets flipped. So, for example, if we have A, B, and C over here, then we get A, B, and C XOR A times B popping out the other side. Similarly, if we ended up having, say, the gate like this, with A, B, and C in Dirac notation fed in, then what we end up getting is we would end up getting A coming out here, B exclusive or AC, and C coming out here. All right, so that's what the controls end up meaning. It means only apply the target gate if both of these bits are 1. Now, we can also express this more broadly as in the following form. We could put an X here. Now this over here is used in order to denote a controlled arbitrary gate. So if gates the top and bottom bits are 1, then apply the gate over here. So this is one way you can kind of start thinking about applying if-then clauses in your logic. You end up using these controls in order to be able to implement it. Okay, great. So that is how controlled NOT operations work. It turns out that, again, once we get to universality, we'll see that actually we don't need, in principle, the Toffoli gate, depending on our gate set. It suffices to have single qubit rotations and C0 to be able to do everything, where this is C0. Okay, great. So now let's prove some properties about these, just to build some familiarity with these types of diagrams. So, first up, I want to be able to convince you that this relationship is true. Okay, that this is actually the same thing as this over here. Okay, so simplest way to prove this is that we can say that two unitary operations are equivalent if they end up having the exact same action on every computational basis state. So the way that I'm going to prove this is I'm going to actually literally do that. I'm going to say, okay, well, let's put an arbitrary computational basis state in. I'll call it A up here, tensor B down there. So if we go through the sequence of operations for the leftmost one, we have A, B, maps to not A, B, maps to not A, B, exclusive or not A. All right, great. Now let's go on the right-hand side with A and B up here. Now, on that side, we have A, B goes to A, B exclusive or A goes to not A, B exclusive or A not, and that is equal to B exclusive or not A. So therefore, because this map has exactly the same action on both inputs, well, that is enough in order for us to say that we have precisely the same map. So this is a complete proof by linearity and the fact that the basis is complete. Now let's take a look at another example. Let's look at feeding in. My next claim is that, or I guess another way of looking at this is if you have an X gate that happens before the control, then the X gate propagates outwards. So, for example, a consequence of this, which is relevant in error correction, is that if you have a sequence of gates that ends up looking like this, and you put an X gate up here, then this X gate propagates, in effect, everywhere out here. It kind of ripples forward through the circuit. Now, interestingly enough, Z gates, or Z gates, as I should be saying in this country, have the opposite rule. Okay, so Z gate ends up actually back propagating through the system. So this is equal to Z C naught, oops, Z over here. Okay, well, and the way we see this is actually really straightforward. If we start with inputs A and B over here, then we have A, B maps to A, B exclusive OR A, and then this maps to A -1 to the B exclusive OR A, B exclusive OR A, because Z will end up kicking back a phase if and only if this bit is 1. So that's why we get -1 to the B exclusive OR A popping up. Now let's take a look at the other option. We end up having that A, B for here ends up mapping to A, B, -1 to the A, -1 to the B, equals -1 to the A plus B, A, B, and that actually is equal to, because of the fact that -1 squared is equal to 1, that's the same thing as -1 to the A exclusive OR B, A, B over here, and then applying a final C not gate maps us to -1, A exclusive OR B, A, B exclusive OR A. Therefore, they're equivalent because they have exactly the same action on every computational basis state. So that's one way that you can end up proving the equivalence of quantum circuits. So now let's go through a little bit more of a complicated example. Another neat one involves how Hadamard gates end up transforming controlled NOT operations. So actually, if we end up having a controlled NOT operation like this turns out to be equivalent to the following. So you can use Hadamard gates actually to flip the direction of a controlled NOT operation. So this is actually quite useful in many examples of near-term hardware, because some devices will only actually give you one direction for a controlled NOT gate. And using this rule allows you to flip the direction without having to have the opposite form of the gate. So how do we carry this out? Well, in order to carry this out, we'll need an intermediate step. And this intermediate property, I probably should have labeled these, but, let's call this A over here. And property B that we'll need is, it turns out that following is true. That if we do a controlled Z operation going up, this is equal to a controlled Z operation going down. How do we see? Where again, a controlled Z operation ends up mapping A and B goes to -1 to the A times B. A, B. All right, cool. Well, one of the things that you can note is that the top gate will do that mapping. The bottom one will map A, B from this exact same logic to -1 BA, AB. But because AB equals BA, these two are equal. So we have that a controlled NOT Z gate is of this form. Next thing, let's modify this this a little bit. So I want to be able to write a controlled Z gate in terms of a controlled X gate. My claim is that controlled Z with two Hadamards around it is equal to a controlled NOT gate. Okay, well, how do we see this? All right, well, let's take a look at cases. Case 1. Let's say there's A and B coming in here. Case 1, A equals 0. Well, if A equals 0, then this circuit is equivalent for that input to the circuit where there's no control whatsoever. Or, sorry, nothing's there because that gate doesn't fire if this is 0. But Hadamard squared equals identity, so this just ends up yielding a B. Okay, so in the case where the top bit is 0, this ends up performing the identity map, which is the exact same thing as C0. So C0 maps 0B to 0B for all B. So this map does the right thing for half of the cases. Now, let's look at the other half of the cases. Case 2, A equals 1. So in this case, what we have is we end up having that the input circuit effectively is exactly the same as H, Z, H, acting on B. And this is equal to 1, X acting on B, using the property that we proved earlier, that HZH equals X and vice versa. Great. So, and this C0 has the exact same map. It maps 1B to 1 not acting on B. Ergo, these two are the same. So now we end up having that Z H equals C0. All right, cool. So then in that case, let's just simplify this. So that also ends up implying, because we can flip the direction of a control Z, this is exactly the same thing as putting an H here and an H here, right? Because all I've done is I've used this property here, property B, in order to flip the direction of the Z gate in the middle, or the controlled Z gate. Cool. Now, using this intermediate property, I can express this as H Z I'm sorry, okay. Getting my steps a little bit confused here. So, what we ultimately want to show is we want to be able to show the identity where the bits are happening on the control. So going back to the case where we have H, C0, H going down, using the above identity, this is the same thing as H, control Z, H, H. This is the same thing as H, Control Z going up, with H's on the other side, and 2 H's down here. And this, using the previous claim, ends up yielding that. And therefore, we've proven our result graphically. So that's another way that you can prove circuit identities. And for the next homework, there's going to be a number of circuit identities that I'm going to get you to prove using one of these two techniques, or heck, if you can think of something more clever, you're more than welcome to it. But those are the two standard ways that you do this. All right, great. So now let's go on to some examples of this. So in order to kind of understand why we need to talk about controlled NOT gates, I'm going to spend a little bit of time, only a tiny bit of time, talking about the concept of entanglement. So, for example, what we end up, let's consider the case of Hadamard 0, tensor product, Hadamard of 1. This state over here is what we call a product state. Because of the fact that it is a tensor product of two individual states, you can see this as meaning that both of them are kind of independent. So they act on different spaces, they can both be queried individually. Measuring one, it turns out, gives you no information about the other. So that is entanglement. This is what a product state is. And so, for example, you can really clearly see that these are two kind of independent states when they're expressed in tensor product form. But when we combine the two, what we end up getting is one tensor product with one negative one, which is equal to 1/2, 1 minus 1, 1 minus 1. And looking at this, it may not be necessarily immediately obvious that there's this independence of the two qubit spaces, but that's manifest here. Similarly, there's actually some states where, although in this case, we can take the arbitrary vector and decompose it into a tensor product of 2, we can't do this in general. And states that are not product states, which are the vast majority of quantum states, we call entangled, which is basically, think of it as meaning correlated, except there's some stronger correlations that can pop up with entanglement than ordinary statistical correlation. So, all right, cool. So that is what an entangled state is. And an example of an entangled state would be, say, the state that's prepared using the following circuit. A Hadamard acting on the top one and controlled NOT acting on the bottom one. When we go through the arithmetic in order to work out what this state is, it turns out it can be written in Dirac notation as the following. It's a good exercise to go through and verify that you understand why this works. But in any case, that is the state. This state, it turns out, actually is not expressible as a product state. And the reason why we can see this, that this is entangled, is, all right, let's say what I want to do is I want to explicitly write this as a product state. So if it is a product state, then there will exist some state phi and some state psi over here, such that this is true. If they're equal, then their inner product has to be 1. So in that case, phi psi 1 over root 2, 0, 0, plus 1, 1 equals 1. This implies that phi 0 psi 0 plus phi 1 psi 1 equals square root 2. All right, now there's this wonderful, wonderful, wonderful inequality. For those of you who haven't used it yet, if you're like me, this inequality can very well change your life. And what this inequality says is that for a sequence of two functions, or two sequences, fi and gi, this is less than or equal to the square root of the sum of absolute value of fi squared, absolute value of gi squared. So what this allows you to do is if you've got a correlated product that you're trying to sum together, you can upper bound that sum in terms of the products of the squares of the uncorrelated sequence. In this case, you'll note that this is exactly of that form. And so this is less than or equal to square root sum over I phi I absolute squared times the sum over I psi I absolute value squared, where these are the coefficients of the quantum state vector. But that is equal to 1 times 1, because the sum of the squares of these coefficients is always 1 by the definition of a quantum state. So that is equal to 1. Therefore, this is a product state if and only if 1 equals square root 2. And implies by contradiction, it ain't. Great. So that is an example of an entangled state. Now, entangled states are phenomenal resources for communication. And in fact, that's what I'm going to be showing you next. I'm going to be showing you a protocol called quantum teleportation. Great. And so quantum teleportation is basically a protocol that ends up working like this. Imagine we've got two people, customarily named Alice and Bob over here. Okay? So let's say Alice and Bob know that sometime in the future, Alice is going to want to send a quantum state over to Bob. But what ends up happening is they've got a quantum channel connecting the two of them, and a classical channel, like a telephone, for example, connecting. Now, this quantum channel, let's say that they know that it's available right now, but later on, there's some other person who's going to be using it, and they may not be able to actually send the quantum state across. And Alice wants to be able to, well, is going to need some time to prepare her state before she can send it on to Bob. So what they can do is they can actually pre-cache their communication by sharing a bell pair. So by sharing, to begin with, half of a bell pair, which I'll write 0A, 0B, plus 1A, 1B beforehand, and the A and the B mean that this part is specifically controlled by Alice. So Alice will only hold on to that part of the quantum state, and Bob will only hold on to the other part of the quantum state. And this is all the communication they'll need beforehand, apart from classical communication, to send the state across. Now, obviously, they could send the state across. For example, let's say what they had is Alice has some quantum state up here, psi. They had a junk state down here, and Bob has a state 0 down there. By swapping this over here, and then Bob swapping it back, Bob could end up getting a copy of Alice's state. Okay, fantastic. But the problem is that in order for this to happen, the swaps have to occur after the state psi is prepared. With quantum teleportation, all of these interactions can be moved before the state psi is prepared. So this allows you to pre-cache all the communications you want and then freely send quantum information between two parties without having any form of a quantum channel or quantum communication path between the two. And that's one of the reasons why quantum teleportation is incredibly useful in quantum communication, as well as parts of quantum information processing. So, the way that this ends up happening is using a property of entangled states. So entangled states, one thing you can see from an entangled state is that it actually doesn't keep its information locally. So ordinary states, like a product state, like of the form psi phi A, psi B, all of the information about phi is held by Alice, and all of the information about psi would be held by Bob, because they're both tensor products, they're independent. But if you have an entangled state, then neither party, it turns out, holds all of the information. And in this case, it turns out if you try to split this up, you can see that actually Alice individually has no information about Bob's state, or Bob's half of it whatsoever, from just hers. So, or more accurately, okay, never mind. I'll explain that more in a subsequent lecture. So, the quantum teleportation protocol looks as follows, okay? We begin with Alice holding a copy of a quantum state, like this. Or, let me actually draw it a little bit differently. We begin the protocol with Alice holding an empty qubit and Bob holding an empty qubit. They begin by preparing an entangled state, like the maximally entangled state that we generated previously using a Hadamard and a controlled NOT gate. Next, after they've done this and they've split their half, then Alice ends up preparing her state psi. Alice does a controlled NOT operation down onto her qubit. Next, she performs a Hadamard gate. So it looks like the inverse of this preparation circuit up here. Okay? Then, what Alice does is she measures. Now, I previously described this operation with an M. In circuit language, it's often drawn as a meter of that form. Okay? Then, she measures her other quantum bit down here. And what she does is she classically sends the measurement outcome to Bob. And then Bob will, if 1, apply X. So think of this as just like a quantum control, except it's controlled by the measurement outcome. And similarly, she sends this measurement outcome to Bob, and if that one is measured to be 1, then Bob applies a Z gate. And it turns out that if he does this, then Bob will end up with a state psi over there. So this can be used in order to be able to teleport a state between the two parties. Alright, well, let's see why this works. So, tracking through the algebra, we end up having, I can always express this as psi 0, 0, even though temporally this state psi is prepared later. I'll begin like this just for convenience. This ends up mapping to 1 over root 2 psi times 0, 0 plus 1, 1. Okay, now I've made it as far as here. So now I'm going to need to express psi in the computational basis. So expressing psi in the computational basis without loss of generality, I can write it in the form A0 plus B1 because it's a single qubit state. So putting that in, I end up getting 1 over root 2 A0 0 0 plus 1 1 plus B1 0 0 plus 1 1. Okay, great. Now, what we end up doing is we perform a controlled NOT operation between this and that. So doing a controlled NOT operation ends up yielding 1 over root 2 A. Now nothing happens on this first branch because the control bit is 0. Oops, plus 1 1. And over here, the middle one's going to flip because the control bit is 1. 0 plus 0 1. Okay, great. Now, the next step is we perform a Hadamard gate on the top line. So Hadamard on the top line ends up giving us after refactoring everything, we end up getting 0 0 A0 plus B1 plus 1 A1 plus B0 plus 1 0 A0 minus B1 is 1 B negative B0 plus A1 is the result. Okay, cool. So now let's say that Alice measures this this qubit, and she measures this one and this one to be 0. Okay, what happens is you can see the action of measurement. When you do partial measurement like this, your state, psi, ends up getting mapped to the following. Tensor I over here. So basically what I'm saying with this is that divided by length. So because you've got to always, after every measurement, have a unit vector. So what I'm saying is that when you perform a partial measurement, that's not enough information to fully reduce the quantum state down to a definite value. If you measure the first two to be 0, but you don't measure the third, what you do is you project the state onto the state that has the first two to be 0. Now, I wrote this over here like a binary tree. Okay, so the first one is 0, second one is 0 here, and then the remaining state is this guy over here. And so if Alice measures 0 and 0, then Bob's state, 0b, or Bob's state over here, goes to psi b equals A0, B plus B1B. Okay, cool. So what this means is in the event that Alice were to measure 0 and 0, then Bob would immediately get a copy of this state. All right, cool. So now, what if Alice ends up measuring 1, or 0, 1? In the event that she measures 0, 1, then we end up with this and this occurring. So the state that Bob ends up with is psi b equals A1 plus B0, which you'll note is the not of this. So this can be fixed by applying X. However, Bob knows what Alice's measurements results are because they're sent. And that's what this apply X here means, is that if Alice ends up measuring 1 in that case, then she sends the result and Bob flips the bit. All right. Similarly, if Alice measures 1, 0, then the state that Bob ends up getting is this over here. He ends up getting A0 minus B1. And that is equal to poly Z A0 plus B1. Okay, equals Z psi. So Bob ends up getting the correct state, but with a poly Z gate in it. And well, what do you know? Because Bob has been sent information about what Alice's measurement result is, he knows that this is a 1, that there's a Z gate that's been applied in the transfer process, so he can undo that by applying a Z himself. And that is what he does. He kills this by applying a Z. Okay, in the final case, it's obvious what ends up happening is a Z and an X. And so we can correct that by applying both of them. And that's quantum teleportation as a whole. The idea basically is that you send, at a high level, 2 bits of information and half a bell pair are used to transfer a qubit. And the cool part about it is that in some sense, this qubit can be transferred over a telephone line, right? Because of the fact that you've sort of pre-cached your ability to transfer information by using a non-local entangled state. And that's what kind of evoked this notion of, or this term, quantum teleportation. Even though, because of the fact that the information that Alice has to send to Bob to make this work has to be transmitted over an ordinary phone line, it almost feels like it's some kind of teleportation. Now, I have to warn you, this is an area where science fiction often goes horribly, horribly awry. People often end up making claims that faster-than-light communication is possible using quantum entanglement. But actually, you can see that in this case, the entangled pair shared by Alice and Bob doesn't allow any transfer of quantum information unless there's this classical communication of the measurement values between Alice and Bob, because otherwise there's going to be a random bit flip and a random phase flip applied to your data, which you can show kind of close to maximally scrambles your data. So that's teleportation in a nutshell. But there's also actually another version that can be thought of. And this version is kind of the inverse of it. It's called superdense coding. And the idea basically behind this is what you want to do is you want to send half a bell pair to send 2 bits of information between Alice and Bob. Okay? And so the circuit, actually, for superdense coding is very similar. First thing, Alice and Bob begin by preparing their states as they're wont to do in the 0 state. Then they begin by preparing a bell state, or a maximally entangled state. The two words are equivalent. Then Alice, who's trying to send 2 bits of information to Bob, encodes those bits classically by choosing to apply a NOT gate over here. The value, I'll call it B2 up here, and then apply a Z gate with value B1 over there. Now we are going to do a controlled NOT on this side, Hadamard gate, and Bob is going to measure out both of them. And my claim is that deterministically, this measurement result is B2, and this measurement result is B1. Okay? So, that's the idea behind this. Or I guess I should say, actually, 1 bell pair is sent, and that can carry 2 bits of information. So, the way that this ends up working is that Alice, or actually, the circuit over here, we can prove that this measurement result ends up holding by actually just using circuit identities. So, the circuit identity that we're going to use first is that poly Z acting on a controlled NOT is the same thing as controlled NOT acting on poly Z. The reason why this ends up happening is because of the fact that the Z is acting on the control bit. So you can go through case analysis and see that in both cases it doesn't matter whether the controlled NOT happens first or later, because the Z gate doesn't change this bit value. It's the same thing as doing it before as it's doing it later. So these two operations end up commuting. So we can have that, and then using that identity, what we get is we end up getting that our circuit can be written in the form X classically controlled B2, C0 going down here, Z classically controlled with B1, Hadamard up here, and then we measure and measure is the equivalent circuit. All right, great. So now what I'm going to do is I'm going to end up using the following identity. I'm going to insert the value 1 just by applying Hadamard twice here. Okay, great. Oh, and this is classically controlled with value B2. So now, what we have is we have that this actually is the same thing as H B2 going down here, and H here, and now X applied with value B1, using our fact that the Hadamard transformation conjugated around Z ends up giving us a poly X operation. Okay, cool. So now we can use our handy-dandy property that x propagates to either side of the C0, which we proved earlier in the lecture. Okay, this ends up giving us x b2 Hadamard x b1, and then down here we've got x b2 feeding off into 2 meters. Great. Now, because this is self-adjoint, this is equal to 0, 0, x b2, and this is z b2 followed by x b1 fed into 2 meters, which is exactly equal to b1 b2 fed into 2 meters. And there you have it. So that's how the converse of this in the form of superdense coding can be done. So next lecture, those are some examples of how you can use entanglement and various other quantum properties to facilitate communication. So in the next lecture, what I'm going to be doing is I'm going to be showing you how to use these gate operations in order to be able to implement an arbitrary unitary transformation. I.e., what I'm going to be doing is I'm going to be showing a universality for the circuit model. And in particular, I'm going to be looking at the circuit model using C0 gates and single qubit rotations. Then, once we're done with that, then we can begin going on to quantum query complexity and understanding algorithms like the Deutsch-Jozsa algorithm, and moving all the way down to algorithms like quantum Fourier transform, phase estimation, and the rest. So thank you very much, and yeah, I will see you later.